rock and roll, everyone. Cool. Yeah, so while waiting, I have here, please pick up your the lecture summary sheet, and there's a handout from section 9A to section 9D, and for those who need the hard copy, let's give those the priority, and then if there's anything left over, feel free to help yourself. Yeah, you can go ahead and pick up the hard copy and also the lecture summary sheet. And I'd like to mention something that Casey just informed me. So when you look at report 4 problems, right? Particularly Casey, he was very more ahead of the class, so he already looked at problem 4.7, and he noticed that the link to section 25E, you know, it says, sorry, the file you have requested does not exist. That means that I had updated this version and had a new version. And the way you look for a new version or the latest version in case you see something like this is to go to the portal and go to the list of my list of topics and lecture notes, right? So that's the link there. And when you go to the list of topics, you can search for section 25E, and then you would see section 25E here. When you click at the link, it should bring up for you the latest version. Okay, so that's how you would deal with when you encounter these that link. Okay, but you know, my lecture notes are always there. Okay, I have also updated the list of active learning credits from last meeting, so you can verify whether your name would be on, and that's this item, okay, for today's lecture summary. And there's a hard copy lecture notes, as I mentioned. In fact, it's from section 9 to section D, okay, not just 3 sections, but actually 4 sections together. So feel free to pick up the hard copy of my lecture notes, and I have also here, as a measure of good communication of ideas and facilitation of learning, provided the exam statement 2.1 and 2.2 well ahead of the exam. Okay, so please prepare, and it has all of the questions very similar to 1.1 and 1.2. All right, we already addressed several questions or you know, some problems in these topics, in these exam statements. And I'd like to bring up, let's see, yeah, so this is known, this is known, I mean, for now I'll bring up, I probably will need to bring up the report 4 problems soon, but just to no, sorry, I made the wrong link here. It should be probably, that was finite element. Okay. It should be so this is the list of topics, or the topics covered, the presentation slide. Okay, week 9, and actually there's week 10 also. We are in week 11, so I have not filled up that yet. Okay, so let's see my goal is to provide you with solution guides for the problems. Let me make this. Okay, so here this way you can scroll. 4.1 there's nothing much. 4.2 there's really, I don't want to say anything more because the statement of problem should be self-explanatory in addition to having the solution guide. Okay, so you can read through, and everyone took mechanics of material, so all of these was supposed to be very familiar. The new thing is how to connect mechanics of material to eigenvalue problem. That's really the main goal of this. And my point is that you can rederive, obtain the expressions for the principal stresses and principal direction by solving the eigenvalue problem. Okay, that's a beautiful connection there. And so please work through. And I welcome all questions. Okay, so all questions are welcome. And I'll be happy to explain when and if necessary. Okay. Now 4.4 I have already gone through. Oh, okay. So let me complete this. This requires section 9D as well, but you know everyone would be very familiar with integration by parts already. So let's see. I need section 8C, right? For yeah, so this is street fighting projection that I already started in the last lecture, and I want to complete now. So you have my code. Essentially, you just copy and paste my code into your MATLAB window, and you get the same result. Okay, so that's really, and you can, you know, if you're not familiar with MATLAB, you should, you can learn from my code as well. And so I have gone through this. The point here is that if you approximate x to the power 5, let me zoom in. If you approximate x to the power 5 by a combination of 1 or x to the power 0 and x, okay, that's a straight line, then you have this straight line here is the least square approximation to this blue curve, okay, in the least square sense, meaning that the square of the error will be minimum. And well, mathematically it's a beautiful theorem that one can prove, but like I said, I want to focus on the street fighting method, so for the larger majority of the class who would be less interested in the higher flying theoretical math, so that you can have, you know, a practical application. Okay. So the next step is to approximate the same function, but now using 3 basis functions. So you would expect that you would have a more accurate approximation, and here it is. Okay, so you see that the purple curve is now better approximate the blue curve, right? Again, in the least square sense. All right, and so then you know, just continue. And now let's see what I do next here. Now let me bring up the mask. Increase to 4 basis functions, right? From B0, B1, B2, and B3. So 4 basis functions. So that means 1x, x squared, and x cubed. Now approximate x to the power 5 by a cubic polynomial. That's what it is. And again, let's recall that the goal of this game is to find the components, meaning the coefficients, in the expansion, just like for vectors, right? For vectors, when you look at an oblique coordinate, I showed you a method to find the components of any given vector relative to a basis of non-orthogonal vectors. Okay, Now, generalizing to functions, an example, or maybe this is a good critical thinking question. What is the equivalent of a non-orthogonal basis of vectors for functions? It's written there. What, just participate. So let me pose the question again, right? So in the case of vectors, you have two types of basis, right? One is orthonormal, that's Cartesian, right? And the other is oblique, that's non-orthogonal, right? Maybe let me pose this question here. Let's maybe section 8b perhaps. Okay, so talking about this reminded me of the following. When I pose a critical thinking question and no one in the class could answer, that means that I had gone pretty fast, not slow. So if you think that you know the answer, or if the class know the answer, well, provide the answer, then we can cover more, we can go faster. If not, then actually the lecture was very fast, right? Critical thinking question once more. Vectors, just vectors. What would be the properties of the gram matrix, which is written here, and repeat it up there once more? When you have an orthogonal coordinate system, Cartesian, orthonormal. What do you expect to see? Okay, so we have Colton. Anyone else? Okay, I need to let me bring up my list of okay, so I can get all of you. Think about and raise your hands. I take all students with your hands raised. What is your, I know, from T2, what is your?
William,
T3, William, anyone else? Okay, so let's start with William and then we'll go to Colton. William, what would be the property of the gram matrix? Right? When you have an orthonormal basis of vectors.
Well, when it's orthonormal, when you multiply by the inverse, then you get the identity matrix.
When you multiply by an inverse, then you get what?
The identity matrix.
Identity matrix. Actually, you can get the gram matrix is an identity matrix. You don't need to multiply by any inverse, right? Why do you? Colton?
For the orthonormal basis vectors, it's going to be a diagonal matrix.
Nice.
Diagonal, but actually identity. By orthonormal, meaning that the length of each basis vector is equal to 1. So what the discussion was that if you look at this matrix here, okay, if the basis is orthonormal, then this is equal to 1. The off-diagonal coefficients are equal to 0, and the length of B2 is also equal to 1. So therefore, for an orthonormal basis of vectors, the gram matrix is an identity matrix. What would be the properties of the gram matrix for an oblique basis of vectors? So we have Robert. Anyone else? Come on, this should be faster. We have Kevin. Anyone else? Okay, so let's start with Robert, and then you go ahead, Robert.
It would be a non-symmetric matrix. So
non-symmetric matrices. Let me note down. We have William, team 3. We have Colton, team 2. And we have Robert, team 5, right? Team 5. Okay, so Robert said that the gram matrix would be non-symmetric. Kevin?
I hate to be a dick, but it would be symmetric.
It would be symmetric, yes. Anything else, Anderson?
If it'd be symmetric, it just would not be the identity matrix.
It would be symmetric, but
It would not be the identity matrix.
would not be identity metric. That's right. So you know the property of symmetry, and Anderson is team 7. Kevin is team 7. Yeah, you know the property of symmetry does not depend on whether you have orthogonal basis or oblique basis. It's a property of the dot product or the scalar product. Okay, Casey asked that question some lectures ago. And so the only thing that is different is that the off-diagonal coefficients are not 0. That's it. That's the characteristic of a non-orthogonal basis. So now let me go back to my original question. When we generalize all of these concepts to functions, what would be the equivalent? What would be the equivalent basis functions that are not orthogonal to each other? Oh, it's written there. And why? Anyone? It's written.
I don't understand the question.
Okay. You know that my goal has been always to drive, into the student that functions can be generalized to, vectors, concepts in vectors can be generalized to functions, right? So that's why we talk about basis vectors and we talk about basis functions. Okay, they are linearly independent, and what does it mean linearly independent? Well, we get deeper and deeper and deeper, and I say, okay, that's enough. You have an intuitive idea or an intuitive understanding of the linear independence of basis vectors. Okay, maybe let's ask this question. What does it mean, two vectors that are not linearly independent with each other? Can you give an example of two vectors that are not linearly independent? Anderson?
2 and 2 and 4 and 4.
2?
So if you have a vector 2, 2, and a vector 4, 4, those are...
2, 2, 4, 4. Okay, that's... Okay, Anderson gave this... okay, very good. Let me bring up my handwritten note. Okay. And while I do this, think about what Anderson just said, right? He said 2, 2, 4, 4. Okay. And... okay, so what Anderson was saying is, okay, so let me type here, give an example of two vectors that are not linearly independent. Okay, and Anderson gave the following example. Two, 2, and 4, 4. Okay. Can you explain? I mean, can the class, anyone else, explain? And let me begin by giving an example. Let's say, let's call this A, and let's call this B. Okay. Anyone else? Kevin?
Well, even though they're unique vectors, they're just scalar products of each other, right?
They are not scalar product of each other. Okay, let me give a hint, unless someone else see this.
Isn't B just 2A?
Very good, yeah.
That's
B
what I'm
is
saying.
2A, so what does it say?
It is a scalar product.
That's a scalar product, am I wrong?
Okay, it's a scalar,
It's not
not a
a dot
product.
product.
No, not a dot product. You were right in saying that this is 2A. Yeah, that's correct. How do you characterize geometrically these two vectors? B equal to 2A. They are collinear, they are parallel with each other. Okay, so geometrically, if you are asked to plot, a picture is worth 1,000 words, right? Then this would be the picture. Okay. This is an example of two vectors that are not linearly independent, and this is an analytical way to see it. So there's a geometric way and there's analytical way. But what is the concept behind this? Why do you need to have a basis of linearly independent vectors to work with? Why can't you work with these? Anyone?
Well, you'd only be able to tell where it was just on that line alone.
Exactly. You cannot define the coordinates of a point, right? You cannot just use these. And so the same thing for functions. That's the power of being able to connect the similarity between different things and the difference between similar things. Remember Montesquieu? Okay. So there's more and more rigorous proof and mathematically how to characterize vectors and linearly independent vectors and things like that. But I just want to stop here because you have an intuitive understanding already, okay? And like I said, most students and people in the outside world, this is enough. Okay, street fighting. So let me pose the question once more. What is the equivalent, concept of non-orthogonal basis for functions? Okay, maybe if I show you the previous page, I hope someone can see. You see, like I said, until you are able to answer critical thinking question, then the lecture was too fast, not too slow. Anyone? This is a very big hint that is under your eyes. Then
It has to do with the fact that since they're not orthogonal, therefore their gram matrices won't be identity matrices.
very good. That's what Anderson was saying. That's what we were just discussing. And this is just generalized one step to functions. And it took a while to have a student mentioning that.
What did he say?
Okay, so let me repeat what Devane said. Okay, and Devane is team 6. Devane said, the polynomial basis. Polynomial basis means 1x, x squared, x cubed, and so on and so forth, right? Is an example of a non-orthogonal basis of functions because the gram matrix was not diagonal. If the gram matrix was diagonal, meaning the off-diagonal coefficients are 0, then this basis is orthogonal. So therefore, the equivalent of an oblique basis for vectors is the polynomial basis. Okay. There's also the equivalent for the Cartesian basis, and that's the Fourier basis. The Fourier basis functions are orthogonal to each other. So when you construct the gram matrix, you have a diagonal coefficient. Okay. So that's the deeper concept. Computing is really low level. That's the lowest level that one can have, because if one just have a recipe and copy the recipe like a solution guide, is really not true understanding. Okay, true understanding is like what Montesquieu said, being able to connect seemingly different concepts and make the connection. Okay. So and so here you see this is the result of the approximation of x to the power 5 by a cubic polynomial, and you see that it's a much better approximation, right? So now you can have no problem, I hope, to do problem 4.4. Okay. Now there's one more thing that you need to know is of course integration by parts. Because why? Let me check. Okay, let's look at the exponential function here in part 1. All right. And KZ, please remind me of the misprint I had in 4.5. Yeah, because I may forget. So let me test the class once more here to see whether there had been complete assimilation of the concept. So now you want to project the exponential function on a basis of polynomials, and from over the interval from 0 to 1, right? And if you define b I x as x to the power I, with I going from 0, 1, 2, dot, 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 right? Then on the right hand side, you need to form the dot product, I mean the scalar product, not dot product, right? Because these are functions. Let's say between b2 and f, right? And in this case, b2 is x to the power 2, and f is exponential of x, right? And let me move forward. So, and that's the integral from 0 to 1 of x squared exponential of x dx. And you can carry out this calculation exactly by integration by parts. Okay. So you need to review integration by parts, and that's in section 9D. And if I have time, I would go through that, because note that section 9D is actually very deep, because it's not just first I derive a very general expression for integration by parts. Okay, this is up to order n. So this formula is very general. It covers, it's like successive integration by parts. Okay, and I don't want to go through that now, but just to point out to you, and then I show you several examples. For example, here you have x to the power 2 times cosine and x to the power 2 times a sine function, and this is the result of applying the formula. But you can also do integration by part once and then do another integration by part. So second time, and you get this result, the same thing. Okay. So in the integration by part, this is a review here of calculus. You're supposed to know this. Okay. You need to select which function in the product as the function v, and the other is u prime. Remember, the superscript in parentheses means the order of integration. Okay. Let me pose this question that would help to review for you. Instead of just blindly applying formulas, what would be a good strategy to choose which factor as a function without derivative and which factor as a function with derivative? Meaning which one should be v0 or v, and which one should be u prime. Okay, you can select. Okay, KZ, anyone else? This is deeper here, and there's direct. Anyone else? Okay, let's direct start. Okay, direct. X squared should be, well, here I wrote as v, and the other is u prime. But can I choose v as cosine and x squared as u? Can I choose the other way around? Meaning v as cosine and u prime as x squared. KZ?
When doing integration by parts, you usually want to look for the value that when you take the derivative or integral, usually the derivative goes to 0. So like in this case, we can choose the polynomials because when we go through integration by parts, eventually the polynomial will reach a constant, so the derivative of that would be 0. So when the derivative times whatever its integration thing is, all the other parts are now just part of the formula of the answer, not the integral.
Yeah, that's right. So let me repeat. You want to choose as shown here, because when you keep doing integration by parts, eventually x squared becomes x and x becomes 1. Okay, and then 1 becomes 0, and that's it. And but if you do the other way around, it's getting more and more complicated, and you don't get out of jail. You don't finish, because x squared becomes x cubed, and x cubed becomes x to the power 4, and then it goes forever, and you don't end. So the clever idea is to choose the function v, no prime, to be a function that eventually ends. When you keep differentiating, it stops. Okay, so that's the technique. Keep that in mind, because that's very important. It's more important than the actual details of carrying out the integration by parts. Okay, because you have to start by selecting a clever choice. So that's one. And how about this one? You have an exponential and you have a sine or cosine. Which one you want to choose as u prime? You can choose u prime as exponential here, and you can choose u prime as sine. That's KZ. Anyone else? This is actually deeper than the previous question. Anyone else? Okay, KZ.
For this one, when you do integration by parts up to 4 times, you see that the integration actually repeats itself, except there's constants. So you can minus the integration over to one side, and then take that coefficient, so you have like the integration with just your answers, because the repetition of the sine and cosine that happens between its derivative and integral.
Yes, so the sine function repeats itself, right, after 2 differentiation. So therefore, you can have the unknown integral on both sides, and therefore you can solve the system. Okay, so let me just when you put together, let me erase this. On the left hand side, it's just the integration by parts, and on the right hand side, you see that when you differentiate twice, you have the exponential and the sine function appearing again, and you can put the 2 terms together, and I is the original integral that you want to find. Okay, so with this, it's like you have one equation and one unknown, and therefore the result is shown here. Just by dividing the left-hand side by this factor. Okay, and the left-hand side is just this term here, evaluating from A to B. So there are 2 techniques for integration by parts that you want to keep in mind. Let's see. Let's go to this, and so the to do part 1, right? That's the first technique, because this is the polynomial basis. But if you go to problem 4.5, where you have to deal with the Fourier basis functions, right? And I ask to do the exponential and the logarithm. For the polynomial basis, meaning projecting. In part 2, I asked to project the exponential function on the basis of the Fourier functions, and in part 4, the logarithm. And KZ just pointed out to me that I meant to ask you to do only part 4. You see, I cut down significantly the amount, but please don't skip it because this is very important. For example, if you have to do part 2, you have to use the second integration by part techniques, the second technique of integration by part, because you have the exponential times sine or cosine. It's, just look at the report from last semester, you see that it's very long and very expensive, and I significantly reduced the amount of work here, and I hope that you have to facilitate your learning, you have more time to learn, but that doesn't mean that we want to skip this, right? Okay, so, and exam is a good motivation, even though ideally that should not be the case. So I say, do the other part for self-learning. Okay. So I think I have covered and coached how to do the report problems. And I finished section 8C, the street fighting function projection on polynomial basis. I also quickly go through section 9D, on integration by parts. It's deeper, it goes to Laplace transform as well. Okay. So when you take the control course, this would be the Laplace transform is important. But for now, I want to move on. Okay, later on when I have more time, I'll come back. Oh, one more thing. You see section 8C here is not, we completely finished section 8C, but this document here that I prepared, actually, I wrote an email to the class last semester, but I just prepared this document as a Google Doc this semester. And that is in preparation for report 5, where you are asked to project a function on an interval that is not 0 to 1. Okay? When you project a function on a polynomial basis over the interval 0 to 1, the matrix, the gram matrix, is very nice. It's already there in MATLAB for you. It's called the Hilbert matrix. Okay? But if you are asked to project on an interval different from 0 to 1, then you need to do something more. And this Google Doc here is the solution guide, and we'll get there when we get to report 5. But please, when you have some time, you can read ahead and participate in the in-class discussion. Okay. Let's see, in the last okay, so now we move on to this section 9A and section 9B. Again, there are some hard copies here, lecture notes for section 9 to 9A to 9 D. Feel free to pick up, and there's still the lecture summary sheet here, team 3 and team 6. Okay, and I want to note down KZ and Derek. Derek is what team number? 8. Team 8. Yes. And and KZ is team 2. Yeah, you already have here. Okay. So, Fourier series, street fighting Fourier series, and let's see, let me report 4. Yeah, so 4.6. Okay, 4.6 is also long, and I cut down, and I ask you to do everything but report only part 4. Okay. Okay, so part 4. Let me. So this is part 4 here. You see, given you are asked the following question: given a function, is it even or odd? So there's a new concept there: even function, odd function. What are those? And then once you decide, then find the Fourier series. Okay. And I ask you to report only part 4 and problem 12. So that means this. Okay. But do everything, do all parts as a practice and for self-study and to prepare for the exams. Okay. So, what is a periodic function, and what does it mean even function? What does it mean odd function? Right? So these are the topics that I'd like to bring up in section 9A. Okay, so section 9A. It's probably, oh, here. Section 9, same as 9A. Let me give you the big picture, and by having 2 small windows side by side, and then we can zoom in. Okay, so the big picture as shown in this table contains, right, you have Fourier series, you have the motivation. We did all this. We did the projection of vectors and projection of functions as well. So now we go to this part here, right? Arbitrary Fourier. So there's periodic function, transformation of coordinates, Fourier series, and then there's odd and even function towards the end. So on this side, you know, everyone knows what a periodic function would look like, right? Sine and cosine functions, and and theoretically, you know, it's described by this formula. Okay, but I prefer to focus on the street fighting method, more practical, more intuitive, and leave the mathematical, the more mathematical aspect to more advanced students and those who like math. Okay. I'd like to keep this in mind. You know, this is an example of a periodic function and the picture. Not everyone would know, and we'll go back to the transformation of coordinates soon. Okay, now in this page here, there's an important formula. This is the Fourier series. Okay, so this is important. So let me bring up the closed And I have only one concept that I have time for today. So let me bring this up in big window, and I just want to address one concept and we'll continue next time. Okay? So that one concept is the following. So here you have the Fourier series, right? In terms of A0 times 1, and then cosine and sine, right? So remember, 1 is cosine of 0. That's part of the Fourier basis, just like the polynomial. But this is the formula that I want to focus on here. How do you remember? What is the thought process to remember this formula? It could be real confusing. And the best way to remember is to look at a circle where this radial direction is rotating, okay, around the circle with the angular velocity omega. Okay, so therefore this is a periodic phenomenon, right? Now, what is a period? A period is defined when time t. So you see the angle. Yeah, let me bring up the mask so that it's easy to follow. You see, the angle is omega times t, right? Omega is the angular velocity, so the angle is omega times t. So how do you define a period? A period is defined when the radial direction rotates a full circle, okay? And that is when, so p is the period, is time. So when omega times p, sorry about that. I write over when omega times p equal to 2 pi, okay? Then you can relate omega is equal to 2 pi over p. The Greek pronounce pi as p, so sometimes I say p, but I meant pi. So 2 pi over p, that's the order, okay? And that came from this very important mental picture that you want to keep in mind, all right? So lecture summary, please, and we'll continue next time.